In this video, we are going to be going over some of the homework problems that are found in the thermodynamics or the energy unit. The numbers on these problems, the numbers on the problems may not match your packet, so make sure that you match up according to which problem it is. So let's look at this problem. Calcium chloride dissociates in water, so we're going to add calcium chloride powder into 100 milliliters of water. And this means that it's 100 grams. We're just going to make that conversion. And we have our starting temperature, which is our initial temperature, and then we have our ending temperature. Remember to find the change in temperature. You always do the final minus the initial. So first of all, let's do A. Is the process exothermic or endothermic? Well, we see that our temperature goes up, so that is our water temperature going up. That means that the energy is leaving the reaction, going into the water, and because it exits the reaction, this is going to be exothermic. Let's look at the next one. So we're going to be using Q equals mc delta T, and this is for the solution. So I'll just plug each of these values in. So remember, for the mass, you need to add the mass of the water plus the mass of the powder. And then our constant, we're just going to use the specific heat of water. This is a dilute enough solution that'll be just fine. And then our change in temperature, I didn't give myself a lot of room, but we're going to find the delta T by taking the final minus the initial. So the final is 43 minus 20, and we get 23.4. So our units cancel, and we're left with joules. And when I do the math, I should get 10,935 joules. And this is the same thing in kilojoules if you divide by 1,000 as 10.9. All right, let's go on to the next problem. So C, we have changed the answer to show how many kilojoules per mole. This is our formula, kilojoules per mole. And we already know our kilojoules. The only thing that you would need to do is to change the sign, because where B is the solution, on this one, this is the reaction. So remember that whatever heat the reaction loses, that is the heat that the water will gain. So if I have a positive 10.9 kilojoules, and this is for the solution, then that means I'll have a negative 10.9 kilojoules, and this is for the reaction. So we have a 10.9 kilojoules up here, and remember it's negative because now it's the point of view of the reaction. I just need to figure out how many moles this is. For this, we're using just the 11.8, so we're not putting the water in. And I need to add up the molar mass of calcium chloride, and I find that it is 110.9. So I just do this many grams, and I divide it by 110.9 grams and 1 mole. And I find that my moles is 0.106. So I just put that up here, 0.106 moles. And then I can divide, and I get a negative 102.8. Make sure you have a negative. If you don't have a negative, it is wrong. And it's kilojoules per mole. So anytime it asks to do kilojoules per mole, that is the formula that you're going to use. So find the kilojoules, find the moles, and remember to switch the signs. So if my reaction is negative, my solution would be positive, and vice versa. Let's go to the next problem. So we have the specific heat of gold. So remember, that's our C. So in the last problem, we used the specific heat of water. This is the specific heat of gold, and it's asking how much energy to heat up 250 grams of gold from 25 to 100. So I'm going to use my formula, Q equals mc delta T. My mass is given to me, 250 grams. I have my specific heat, And then I do my change in temperature. So remember, it's always final, which is 100, minus 25. So this would be 75 degrees. My units will all cancel. I'll be left with joules. And when I do the math, I get 2,400 joules. So if I did my math right. But again, this is how much heat I'm going to have to put into it. It will have a positive value. Let's do this next one. So calculate the heat released. So I already know that my value is going to be negative because the heat is releasing. It's going to be exiting. Q equals mc delta T. And for this one, my mass, and we're back to water. So that's how many grams of water. I'm going to use the specific heat of water. And my change in temperature. And remember, you always go final minus initial. And I get a negative 75 degrees Celsius. My units cancel, grams cancels, I'm left with joules, and then I just can do my math. And I get a negative 14,891. If we were to do sig figs, we have 3, so I can cut it off there. Not so worried about the sig figs, just that you get the signs right. But this is how much heat that is released when some water is cooled. All right, let's do this one. It says calculate the delta H. So this is the enthalpy. So remember, enthalpy has an H right there in the middle. If it was entropy, that is a delta S. But we're given this formula right here. So we're going to look up each of these values. And one of the values is not on your chart. It's given to you right here. Remember, the formula is to take the sum of the products minus the sum of the reactants. So I'm going to look over here on the right-hand side first. And I have COO, and I already looked up these values. They're right here. So I'm going to use brackets for all of the products. So I'm going to do negative 237.94. And there's just a 1 there. So multiplying it by 1 is just going to be the same thing. And then I add it to 1 mole of the CO2, which is right there. So that's a minus, a positive, and a minus. I'm going to get a minus. So minus 393.90. And these are kilojoules per mole. And then I'm going to subtract the reactants. I only have one reactant, and it's given to me minus 721.9. And so remember, if you have a minus times a minus, it's going to be a positive. And I can go ahead and add these together. I'm going to get a negative. I get a minus 631.449. And then I'm going to, you can see I'm going to end up with a positive number. And I end up with my delta H is a positive 90.4 kilojoules per mole. Okay, so this is the amount of energy that goes into the reaction. This is endothermic. Let's go ahead and go to the next one. So it says calculate the change in enthalpy in kilojoules if 17 grams of the CO3 is used instead of the 1 mole. So you can see up on this problem, we're using 1 mole. Now they're saying, okay, what if you had 17 grams, then how much energy we have? So again, this is for 1 mole, our answer. So for this, you are going to have to use the molar mass. So I need to find how many moles is this 17 grams. So I'm going to use this molar mass. I'm going to get 118, whoops, a little too many. 118.9 we'll say is good enough grams in 1 mole. So when I multiply this out, this is 0.14298. Lots of sig figs here. Okay, moles. And I know from the problem that if I have 1 mole, that gives me 90 kilojoules. So I just have to multiply through and I get 12.9 kilojoules. So again, with that 17 grams, it's just a portion of a mole. So 1 mole would be 118.9. So I'm only going to have a portion of the energy. So a quantity you have, it depends on how much energy. So the greater the quantity, then the more energy is required or will be released. All right, let's look at this next one. So when 10 grams of aluminum melts, it gives me how many kilojoules of energy is right there. And it says, what is the change in enthalpy in kilojoules per mole? So I know that my formula is kilojoules per mole. Anytime it asks for kilojoules per mole, that's my formula, okay? So I already have my kilojoules. And I just need to find my moles. I have 10 grams. So just kind of like I did in that last problem, I need to find out how many moles this is. So looking on the periodic table, 26.98 grams is equal to 1 mole. Grams cancels, and the amount of moles I get is 0.37 moles. So I'm just going to put this in my formula, 0.37 moles. And then I just divide it out, and I get 10.6 kilojoules per mole. So, and I know that because there's a 1 right in here, so that means 1 mole. So 1 mole gives me this amount of energy. So if I just had, again, a portion of the mole, I would just get a portion of the energy. So again, just using some dimensional analysis, canceling units. So right here, I need to make sure my grams are on the bottom. These two quantities are equal to each other. And so then I'm keeping the quantity the same, just with a different unit. All right, so this one is looking at disorder. So remember, disorder is delta S. So if you have a positive delta S, that means you're increasing the disorder. And I remember it's disorder because it's that S, it's disorder. If you have a negative delta S, that means it's a decrease in disorder. It's kind of a double negative. But that's how you can remember it. So again, this is entropy. Again, no H in the word entropy. So I know this is my delta S, okay? So on these, I'm going to be looking at disorder. Remember, anytime you go from a solid to a liquid to a gas, your entropy will increase. So gas has the most entropy because it has the most disorder. So on this one, I have a liquid going to a gas. So this is increasing disorder. So I'll just put a plus. Actually, on this one, it says which has the higher entropy. So let's go ahead and this one has the highest entropy. Looking at the next one, so we have a liquid versus a solid. So liquid is going to have more. On this one, it helps to have a little picture. So this one, it's together, so it's really one thing. And this is separate. So you can see there's more disorder with having the atoms separate. There's more possibilities of where you would find it in its container. If it's together, there's less possibilities. And so again, this one's going to have more disorder. Solid or a solution, that means it's a liquid, so a liquid's going to have more. And this one again is a solid versus a gas. Gas is going to have more. And on anytime you have a equation like this, you want to look at the number of particles or to see if it's going from a solid to a liquid or from a solid to a gas. And on this one, I can see I have 4 moles on this side, and on this side I have 2 moles. So which one is going to have more disorder is the one that has the 4 particles. And these are all gases, so I can't use the state of matter to help me. I'm just going to look at the number of particles that we have. So that is the reactants. Now on this one, you have greater than and less than signs, which I find kind of confusing. So I like to go through and just put if it's negative or positive. So this one kind of has a pattern. And I can do the same thing for my entropy over here. And then a chart that you're going to want to reference during the test or if you have it memorized. So remember to put this is exothermic and this one is increasing disorder. So that's the one that nature tends to favor. So write those first. And whenever you have those two situations, then it's always going to be spontaneous or thermodynamically favorable. So I'm going to put always favorable. That means it will happen. So you might give it some activation energy to get it going, but then it will go to completion or towards equilibrium. And then if you have the opposite, so that would be in this box here, this would be never favorable. That would be like trying to make ice cubes when it's 90 degrees outside. That's not going to happen. Okay, let's go ahead and look at the upper box. So because this is the higher box, it's temperature dependent. So it's going to be favorable if, because it's the higher box, it has a high temperature. And it's relative to the problem, but what means high temperature? So if it just says high temperature, then that's what it's referring to. And then this one, it's going to be favorable if it has a low temperature. So for example, you couldn't make ice cubes with 90-degree temperature, but you could if you had minus 10-degree temperature. So that would make it freeze. So it would be favorable. All right. So if you have this chart memorized, we can tackle this problem here. So we're going to do favorable or non-favorable. So we're just going to try to match it up with this little chart. So on this first one, I have a minus delta H and I have a minus S. So that's right here. And it does say low temperature, so it would be favorable. So I'm going to put an F there. And then let's go to the next one. I'm going to run out of colors really, really soon. So this one has a plus H and a minus S. So we can see it's never favorable. So it doesn't matter what temperature is, low or high. So it's going to be not favorable. And on the next one, we have a negative delta H and a positive delta S. So that's right here. So again, this one doesn't matter what temperature it is. It's going to be favorable. So it doesn't, even though it says it's a low temperature, that doesn't matter because it doesn't matter what temperature it is if you have a negative delta H and a positive delta S. Let's do the next one. So we have a positive delta H and we have a positive delta S, so it's right here. So it's favorable if we have a high temperature, but we have a low temperature, so it's not favorable. So I'll go ahead and let you finish out the rest, but this is how you analyze that. So again, when you go to take the test, have this memorized or have it in your notes if you're taking the test at home, so you have it all ready. All right, let's look at this one. So so there's a couple different ways to solve these problems. We could use Gibbs free energy equation. And then remember, it doesn't matter what you have, delta G or delta H or delta S, you can always take the sum of the products minus the sum of the reactants. So that's what we're going to do, kind of a combination in this problem where we do kind of all of them, do both ways to find it at once. We can take this equation and we can rearrange it to solve for delta S right there, so the entropy. And then looking at our data here, we have a delta G and we have a delta H, and we're giving some values there. And this is a little screwy, but this is that value right there, okay? All right, so I need to find my delta G first and then my delta H, and I need to find them by doing products minus reactants. So let's quickly do that. So notice when I set this up, these values in the chart are just for 1 mole. And so I need to use the stoichiometry. And again, I do products, so I'm going to do 8 times its value. And then you add it, plus 10 times its value right there. And then you're going to subtract the reactants. And remember, for elements, it's always 0. So that gives it right there. So when I do products minus reactants, after you add them all up, I'm going to get this number, minus 5,409.5, and that's kilojoules per mole. And then I'm going to do the same thing for my delta H, but just use the delta H values. So I'll use the ones on the second line. So let's quickly set that up. And for this, I get a minus 5,316. So I'm going to take those values and put it up here. So I have my H, don't forget the negative, and I subtract it. Subtract that G, so it would be a negative 5,409.8. And then I divide it by my temperature, which it says it's 298. So when I do this, my final answer, I am going to get 0.315, and this is kilojoules per mole divided by degrees Celsius. Now notice it's really, really tiny, and that is because delta S is usually very small, especially compared to your delta H and your delta G. That's why your delta S is usually expressed in joules, not kilojoules. And you can rearrange the units so they're not so difficult there, but that would be one way to represent the units. So again, very, very small number. If you were to convert this to joules, it would be 315 joules per mole.